Universidade do México. A professora Rosa Maria obteve seu doutorado na Universidade Nacional Autônoma do México. Ela fez, na sequência, um pós-doutorado em Paris, né, no Laboratório de Física da Matéria Condensada, com o professor Pierre Degennes. Pierre Degennes foi Prêmio Nobel de 1991, se não estou enganado. Atualmente, ela é professora emérita do Departamento de Física da Universidade Autónoma Metropolitana, na Cidade do México. Ela tem uma experiência no ensino de física de mais de 45 anos e, atualmente, ela trabalha com modelos de fluxo veicular, ondas de choque e termodinâmica estocástica. Então, eu gostaria de agradecer à professora Rosa pelo seminário, né? E dizer que é uma satisfação tê-la aqui com a gente. So, Rosa, thank you very much, and let's go.
Okay. Good afternoon, everybody. I'm very glad to be with you, and I thank all the organizers for inviting me to this presentation. I think I must begin. Well, the title of my talk is the shockwave structure in dilute gases, and it is a work I have done with Professor Francisco Uribe, which is also at the same university, and it is published in the reference just here in the Wave Motion in January this year. So it's a recent paper. Here you have the abstract I sent you, and it explains the essential topics in this talk. We will work with dilute gases and a shock wave propagating along the x-axis, and we will develop the so-called Linear Irreversible Thermodynamics, LYT, and apply this model to study the density and temperature profiles along the shock. Also, we will compare with the usual Navier-Stokes equations completed with Fourier laws for heat flow, and also the so-called Holian conjecture. I will explain how is it done, and at the end, I will compare all the results with experimental data which were obtained some time ago for helium at Mach number 1.59. Well, here you have just a figure to motivate this talk, where you have a plane which has just reached the speed of sound in air, rarefied air, and this conical figure corresponds to small water droplets which are condensed around the shock. Also, here there is a setup in which actually at the University of Texas, they do some experiments on combustion and chemical kinetics, etc., where the Mach number is between 1.5 up to 4. It is just to give an idea of the kind of experimental setup which is needed to study shock waves in gases or in fluid systems. But now let's begin with the main topic. Here there's an outline of the talk. First, what will be an introduction, then the Navier-Stokes-Fourier model, the Holian conjecture, and then our model, which I called as LYT, Linear Irreversible Thermodynamic Model, and the experimental data for helium at Mach number 1.59. And then some concluding remarks. First, introduction. Well, in fact, we are going through the continuum approach to describe a fluid behavior. When we are working with shock waves, this description starts with the mass, momentum, and energy balance equations in a fluid. Here, there are the equations which are valid in this case. The first one is the conservation of mass. The second one, the density momentum balance equation. And then equation 3 is the conservation of the total energy. Here, rho is the mass density, u is the velocity, this P is the pressure tensor in the system, Q is the heat flux. Also, the energy total has a specific energy total. Total energy is the kinetic energy and the internal energy. And well, here is the pressure tensor and the heat flux. Now, we will consider that we have a plane wave which propagates with constant speed c0 in x direction. And we are interested in a stationary plane shock wave where it is possible to integrate equations, the balance equations, because there is no time dependence. And due to the condition of propagation in only the x direction, we can integrate the equations in a very simple way. Then the first equation which appears here is the density, the flux of the mass density, which is constant. Here, the second one is the density momentum, which is also a constant, C2. And then the last one in equation 1 is the conservation of energy for a stationary case. And after an integration over the position, the quantities C1, C2, and C3 are constants and can be obtained by applying these equations to an equilibrium point, a thermodynamic equilibrium point. In this case, this component Xx of the pressure tensor reduces to the hydrostatic pressure. The viscous tensor, which is a part of this pressure tensor in general, becomes 0. And also, in an equilibrium point, the heat flux is also 0. Then we can solve these equations for the corresponding, for this case, for equilibrium. But our problem is not an equilibrium one. Also, we must complement this set of equations with the pressure and the internal specific energy. There's one here, and the hydrostatic pressure, which is a part of this pressure tensor. And we will choose a monatomic gas, the simplest one. Then the XX component and the pressure tensor becomes just the hydrostatic pressure, and the viscous tensor, also the same component, XX. This is the hydrostatic pressure for a dilute gas, just an ideal gas, and this is the internal energy per unit mass. This is the temperature, the mass of the particles. Well, all those variables are functions of position along the propagation direction as seen from a reference frame which travels with the shock wave. In fact, the shock wave is traveling with a constant speed along the x-axis, but we take a reference frame which is moving also with the propagation of with the speed of propagation for the shock wave. So we see only the position dependence in the pressure, in the hydrostatic pressure and the density and in the temperature. then the set of equations complement these conservation equations are written in equation 4. Well, in fact, equation 4 are called as the Rankine-Huguenot jump conditions. Why? Because in equilibrium points, as I said before, the heat flux vanishes and also the viscous tensor vanishes. And we can show that the conservation equations after the integration has only 2 equilibrium points. In both equilibrium points, these conditions are satisfied. And we can find the coordinates of those equilibrium points by applying the Rankine-Huguenot jump conditions in the 2 points. The coordinates for these points are called as rho naught, u naught, p naught. This is the equilibrium point which corresponds to the cold part of the shock. And normally it is called upflow. And then the index 1 and these coordinates will be the coordinates in the hot part of the shock, which is called as downflow. So the flow is going to happen between upflow and downflow. It means the coordinates of one of the equilibrium points to the other. Now, we will define some dimensionless variables and the Mach number. The Mach number is the ratio between the velocity of the sound speed, we call u naught, referred to upflow, and C0 is the speed of sound. Then this ratio is called as the Mach number. In the gas, monatomic gas, as we are considering now, the speed of sound is given in this simple way, with also the temperature referred to the upflow, to the cold part of the shock. And then we can define different quantities, variables, which are dimensionless. First, the speed of the shock wave is called as its velocity divided by the velocity at upflow, and also the density with the semi-convention, and tau will be the temperature, essentially, also without any dimension. In this way, well, the notation is simplified, and also we can work with these coordinates, reduced coordinates. The position is reduced with a typical length called as lambda, which will be chosen after a little later. The upflow and downflow coordinates can be calculated with equations of conservation, equations 4, which are known as the Rankine-Huguenot jump conditions, as I told you before. What are these coordinates? Well, here you have it. If you apply the equations after the integration to both equilibrium points, up and down, flow and downflow, then its coordinates for upflow is V0 equals 1 and tau 0, which is given in terms of the Mach number, as I will write just before. And the coordinates of downflow are given here with the index 1, where this tau 0 is given in terms of the Mach number, and it is defined here. So the coordinates at upflow and downflow are all defined in terms of the Mach number. So we just need the Mach number to calculate everything here. Also, due to the fact that upflow and downflow are equilibrium points, thermodynamic equilibrium points, we can calculate other thermodynamic properties. In fact, the change in entropy between upflow and downflow can be calculated between those 2 points. And for an ideal gas, like the one we have here, this difference in entropy between the two equilibrium points is given in equation 8, where we notice that this change in entropy has this way to write, and it is the logarithm of these quantities up to the three halves and the both velocities at downflow and upflow. When we substitute these quantities in terms of the Mach number, it is very clear that this change in entropy is positive. It means that there is an increase in entropy in our system. So there are several dissipative processes in between upflow and downflow. Usually, it is the shock wave is considered as a discontinuity surface, but this fact makes us think that there is no necessarily a discontinuity surface. Instead, we can have a profile between upflow and downflow, and we can calculate the final change in entropy between the two flows, but in the middle, between the 2 points, equilibrium points, but in the middle, the entropy can be defined as it is done in irreversible thermodynamics. It means we can have a profile along the shock for the entropy. What it is important here is that there is a change in entropy. This change in entropy is positive, and it indicates the presence of dissipative processes. What kind of processes, dissipative processes, can we have in this case? Well, viscosity and thermal conductivity. And it means that viscosity and heat conductivity will contribute to the profile in all thermodynamic variables or local variables we can define for this problem. It means the density profile, the speed profile, and the temperature profile, among other variables. And this viscosity and heat conductivity, we need to calculate all the contributions, which are the simplest one for a simple fluid like the one we are working with. Now, pues, if we take this into account, then the viscous component in the pressure tensor, we call here as this kind of P, and the heat flux constitutive equations become the most important hypothesis in the model to obtain the density and temperature profiles. It means that these constitutive equations must complement the equations of conservation, which have just obtained before. And these constitutive equations will have the contributions we need to calculate the profiles. Well, now it is time to proceed to obtain a solution of the equations where after we give the constitutive equations for these fluxes. And the first thing we have to do is to choose the reference length I called as lambda. We have found that this quantity is a convenient length to define this typical length. Evidently, this has dimensions of length, and it is given in terms of quantities evaluated at upflow. Eta 0 is the viscosity, the shear viscosity evaluated at upflow, and the density and velocity also at upflow. So with this typical length, we will define, we have defined the position along the shock, along the profile, which we call as S. But also, the usual viscosity, here viscosity and thermal conductivity, are modeled with the soft sphere model. It means that the viscosity, shear viscosity over the shear viscosity at upflow, which we call as an eta asterisk, is given in terms of the temperature profile divided by this quantity tau 0, which is related with the Mach number. And there is an exponent here called a sigma, or viscosity index, which is chosen according to a fit of experimental data, as I will describe before. After. Also, the thermal conductivity is given in these terms, and we will take this shear conductivity asterisk equal to the kappa asterisk, which is also the thermal conductivity divided by thermal conductivity at offlow. And also, the Prandtl number is a dimensionless number which measures a relation between viscosity and thermal conductivity, and we will take as 2/3 this Prandtl number, which is the most usual value for this quantity related with the viscous and thermal conductivity effects. Well, let us return to the constitutive equations after defining these quantities. Well, we need to close the conservation equations, which are given in 1, 2, and 3 equations, in which also the heat flux and the viscous tensor appeared. And then choose the constitutive equations. The simplest ones are the so-called Navier-Stokes-Fourier, which also can be given by a phenomenological way, or we can calculate them with a kinetic approach. For example, Chapman-Enskog, or some other method to solve the Boltzmann equation for a dilute gas. And this is a way to do that, formulate Navier-Stokes-Fourier equations. But also we can take different models to calculate the profiles we need in the shock wave to see the shock wave structure. Then our goal in this work is discuss the phenomenological model we called as Linear Irreversible Thermodynamics model, as I will show you later. Also, we will compare the results with Navier-Stokes-Fourier, the Holian conjecture, and this model, as I said before, and experimental data. Well, in a phenomenological scheme, I said some minutes ago, the simplest way to do that is take the Navier-Stokes-Fourier equations. Here they are in equations 9. Then eta is the shear viscosity, kappa the thermal conductivity, and we have the viscous tensor coupled with the velocity gradient and the heat flux coupled with the temperature gradient in the very simple way. Then we substitute these constitutive equations in the conservation ones and write all these equations in the dimensionless, in terms of the dimensionless variables we defined above, in some equations before. Then we can write the conservation of momentum in this way, with here it is the viscous tensor. We have substituted also the pressure when it is necessary, and write everything in terms of the reduced variables, all of them functions of the position, also divided by the typical length we have just defined. And this one, equation 11, corresponds to the energy conservation equation, in which we have also the pressure, the viscous tensor, essentially, the temperature gradient coming from the Fourier law, and then all other quantities like kinetic energy, something like that. Everything written in the same dimensionless coordinates. Here it is the Prandtl number, which we take 2/3, and these two quantities are equal due to the hypothesis we did in the last page. Then here it is the Navier-Stokes-Fourier equations, which determine the shock wave profile, both the speed profile and the temperature profile. Those are coupled equations, non-linear, because the eta star is a function of also of the temperature tau, and with an exponent which is not necessarily simple. It must be chosen. Then, well, we have that, and we need to solve these equations with some initial or boundary conditions to solve that. But this is one of the sets we use to obtain the profile, and this is called the Navier-Stokes-Fourier, well-known Navier-Stokes-Fourier equations. Going to the Holian conjecture, well, how is it set? Well, Holian, a lot of years ago, more than 20, I think, started also with the Navier-Stokes-Fourier equations. But what he said is that the viscosity and thermal conductivity must be evaluated in terms of the longitudinal temperature instead of the total temperature in the system. This is the definition of the longitudinal temperature. And he took the viscosity, shear viscosity, which here I have an H because Holian proposed that, is proportional to the longitudinal temperature defined here to the same index viscosity as we have before. And also the thermal conductivity in this model, instead of the temperature, the total temperature, then also the longitudinal temperature is assumed to construct this transport coefficients. In fact, when we take the definition of the longitudinal temperature and write it in terms of the variables we have defined before, this longitudinal temperature as a function of position can be written in terms of the speed profile in the shock wave in this way. It is a direct thing to do that. And well, now we can write the equations corresponding to the Holian conjecture, which are the same as Navier-Stokes, but instead of the longitudinal, instead of the total temperature in the viscosity, shear viscosity, and thermal conductivity, we write this function corresponding to the longitudinal temperature instead of the total temperature. And well, it gives two equations, also coupled as in Navier-Stokes, and nonlinear, which also need initial conditions or boundary conditions to be solved. Now, going to the linear irreversible thermodynamic model, we have considered the following hypothesis. We come through the steps in linear irreversible thermodynamics. It means that we adopt the local equilibrium hypothesis to construct the hydrostatic pressure and the specific internal energy, which also is done in Navier-Stokes equations. However, we go further, taking also the fundamental equation in thermodynamics, TdS, but now for a process which is in non-equilibrium as the one of the shock, characteristic of the shock wave. And we take the validity of this kind of equation in thermodynamics, but for local variables. It means written in terms of the variables which are functions of position along the shock. And in this case, we know that the entropy production corresponding to linear irreversible thermodynamics is the product of fluxes multiplied by thermodynamic forces. The fluxes corresponding to the momentum is the viscous tensor, and corresponding to the difference in temperature is the heat flux. And the corresponding forces are essentially the gradient of the speed for the viscous tensor and the gradient of temperature for the heat flux. Well, also in irreversible thermodynamics, it is assumed that there is a linear relationship between the fluxes and the corresponding thermodynamic forces. It means that the viscous flow is proportional to the gradient of velocity, and heat flux is proportional to the temperature gradient. With this hypothesis, we can consider also Navier-Stokes-Fourier model. The connection is direct. Pressure, viscous tensor proportional to velocity gradient, heat flux proportional to the temperature gradient. But in our model, called as EY-LYT, the constitutive equations are written in this way. Now, this is a generalization of what we do in Navier-Stokes equations. Now we have the viscous tensor proportional to the velocity gradient, but also a cross term, which means that here you have the temperature gradient coupled with the viscous tensor. It means that some viscous stresses are produced by the temperature gradient and not only with the velocity gradients. Also, the heat flux has the term normal in the Fourier's law, in which the heat flux is produced by a temperature gradient. But there is also, this is our hypothesis, that there is also a heat flux coming from differences in the velocity in the shock wave. These two terms, which are written in red color, corresponds to the so-called cross effects, which normally exist in irreversible thermodynamics, linear irreversible thermodynamics. For example, in mixtures, in binary mixtures, you have that the diffusion flux is produced by a difference in concentration, but also with a difference of temperature, and you have a cross effect. Also, the heat flux is produced by temperature gradients, but also for concentration gradients. These are the well-known Fourier and Dufour coefficients. But now we don't have a mixture, we have a simple fluid. But what we have in this problem with the shock wave, which has a preferred direction, which is the propagation direction of the shock wave, And we are proposing that there is a close defect between this temperature gradient and the viscous components, and also there is a gradient in velocity producing a part of the heat flux. This is a big change in constitutive equations, but they are consistent with linear irreversible thermodynamics due to the fact that the fluxes are linear combinations of thermodynamic forces, both the viscous tensor and also the heat flux. And we need now to tell what is the way we can calculate these coefficients, both these cross coefficients which affect the viscous tensor and this cross coefficient which affects the heat flux. Well, it is the main assumption in this model. And well, we calculate these coefficients, give them a certain dependency with the temperature, taking as a basis the shear viscosity eta. And with the dimensions of these coefficients must have, according to equations 15 and 16, we found that these cross coefficients might be written in this way. The viscosity, the shear viscosity, the usual shear viscosity, the total temperature, and well, this is the speed, the mean speed associated with a temperature T, with a coefficient which is a constant which must be determined with comparison with a fit of experimental data. And also this coefficient which affects the heat flux caused by the velocity gradient also has the same structure as the other one, but in general, a different constant multiplying these quantities which take into account the dimensions of these coefficients. And here you have the usual thermal conductivity where the Prandtl number was taken as 2/3. Then these coefficients in black are the usual ones, and these in red are the cross coefficients which are new. Now we need a way to determine these quantities A2 and A3. And we have chosen them to fit the experimental data. But before we fit these coefficients with experimental data, there is also an ingredient which is usual in linear irreversible thermodynamics, which is the Onsager's symmetry between coefficients, between transport coefficients. Now, we will take also the Onsager's symmetry and apply this to our constitutive equations proposed in LYT model. Well, to have a feeling about these coefficients A2 and A3, we take the Onsager's reciprocity relations, but we note that those coefficients couple temperature with viscous tensor, temperature gradients with viscous tensor, and velocity gradients with heat flux. And temperature and the speed have different properties under time reversal. So the Onsager's symmetry must be written in its most general form, which is that the cross coefficient LG is equal to these epsilons, which are -1 if the quantity which I refer to is odd under time reversal, and +1 if it is a pair quantity under time reversal, by multiply by the coefficient with the indexes inverted. But temperature and velocity have different parity under time reversal. So one of this epsilon is +1 and the other one is -1. So the cross coefficients A2 and A3 must have different sign, must be equal to satisfy the Onsager symmetry, but A3 equals minus A2. Then because of the symmetry under time reversal of the variables involved in these coefficients. Well, now it means that our model, the LYT model, contains two parameters to fit. One of these parameters is the soft sphere index, sigma, which gives us the viscosity. This one must also fit experimental data. Normally, it is taken according to a fit with ab initio results for viscosity. That's one way to do that. Other way to do that is to take calculations coming from the direct Monte Carlo method, or just have some profiles obtained with Navier-Stokes-Fourier equations and fit this exponent here to calculate the viscosity. Well, this is one of the parameters contained in this model LYT. The other parameter is this quantity, A2 or A3, it's equivalent because they are equal and just the sign is different. And we chose the A2 quantity to measure the cross effects. Then in this model, we have two parameters, sigma and A2. Both are taken from experimental data by means of a fit. Now, if we compare with experimental data, what we have? Well, we substitute in the equations of conservation the constitutive equations we have proposed in LYT model. And then it is obtained two equations which are coupled also. Here B prime and tau prime are the derivatives with respect to S, and all variables here depend on the dimensionless position. So this equation, which comes from the momentum density conservation, has the coupling with the energy conservation, coupling for velocity and speed. Here there is the viscosity written in terms of the index viscosity, which must be fit, one parameter of this model, and here the A2 parameter, which also appears in several terms. In this equation, now, the same as we said before, we need initial or boundary conditions to solve these equations. Well, in this structure written in equations 20 and 21, we can obtain the three models we have just introduced. The Navier-Stokes-Fourier equations can be written with this prescription for the viscosity, and A2, our parameter in LYT, equals 0, then this term disappears, also this one, and if you compare equations 20 and 21 with the ones in the Navier-Stokes model with A2 equals 0, are exactly the same. So we have here the contained in these equations for A2 equals 0, the Navier-Stokes ones. The Holian conjecture is obtained with A2 equals 0, and instead of the viscosity we have used in Navier-Stokes-Fourier, like written here, we have to substitute the temperature here as the longitudinal temperature, and here you have the Holian conjecture. And LYT Well, we have the same hypothesis for the behavior and the viscosity, but A2 must be chosen to fit the experimental data for each particular case. So we have the two parameters which needed in LYT model. Now we will take experimental data available in the literature and compare these three models with the experimental results. The results we have taken corresponds to Muntz and Harnet's paper. Here you have the reference. They are some old data, but corresponding to the temperature profile, there are the only ones existing in the literature up to our knowledge. So this is the ones which we use to compare all the models we have written before. In this case, in this paper, they use helium. The upflow temperature is 160 Kelvin, and the Mach number is 1.59. And then, in fact, Muntz and Harnet assume or propose this value for the index in the viscosity. And, well, here you have the first results. Here you have, in the vertical axis, the velocity as a function of the position, and here you have the dimensionless position. Then, here, well, the figure corresponds to two kinds of things. The first one, there is a dashed line which corresponds to the Navier-Stokes-Fourier solution. This black dashed line which goes there. The long dashed line, that red line, is the one corresponding to our model, LYT, where we have chosen A2 equals to 3 halves and the same sigma as here. And well, see that the black and the red dashed lines coincide. The open diamonds here correspond to our LYT model with the Holian conjecture, as this is calculated. It means that it is calculated with the viscosity containing the longitudinal temperature. We call with these letters here to avoid a very large number. And the black points here corresponds to the data, experimental data, coming from this paper about Muntz and Harnet. You see that there is almost no difference between predictions of the model, the calculation with all these three models, and the experimental data. Obviously, there are some differences, but essentially are the same figure. However, well, it is the velocity profile. However, when the temperature profile is considered, and this is where the Muntz and Harnet paper is the unique reference for experimental data concerning the temperature profile, you have here the results. The vertical axis corresponds to the temperature as a function of position in the horizontal axis. The experimental data are the points. The model Navier-Stokes-Fourier corresponds to the red solid line. The black dashed line, this one, which almost coincides with the red line, Navier-Stokes, is Navier-Stokes-Fourier with the Holian conjecture. And nor NSF or NSH models coincide with experimental data, which are the solid points. However, the LYTH, it means our diamonds are best in comparison with the experimental data. And our model without the Holian conjecture with A2 equals 3/2, which is the red dashed line here, is the one which gives the best agreement with experimental data. So here you have 4 different ways to calculate the temperature profile, and the one which corresponds better to the experimental data is the LYT, with this parameter chosen with as 3/2, which we considered that it was the best fit for A2 in this case. Also, in this paper by Muntz and Harnett, there are the total temperature profile, which is this one, which is called here as average, and also the longitudinal temperature are also given in terms of experimental data, which are these points here, and the dashed lines, the blue one, corresponds to our model LYT with A2 equal 3/2 equal to the other profiles here, which coincides surprisingly well with experimental data, and the average temperature with the same model, the LYT, it is here, and also coincides with the temperature profile given by the experimental data. Here, the blue diamonds are the experimental results for the total temperature, and the black ones, are the longitudinal temperature. You can see that here, the LYT model is, well, I think a very good one when compared with the experimental data. And, well, here you have a fit for the parameters, both the index viscosity and the A2 parameter, which is the new one in our model, which fit very well the experimental data. Well, I say very well. I think it's really, well, it's okay, no? Within certain uncertainty due to the fact that experimental data have also certain uncertainty. Well, concluding remarks. Now we have calculated the speed profiles through the presented models. Concerning the speed profiles, the coincidence with experimental data is very good for all models presented in this particular case, obviously. In contrast, the temperature profile cannot be reproduced either with the Navier-Stokes-Fourier model or the Holian conjecture. But the lead model, LYT model, makes the task no matter if the Holian conjecture is taken or not, as we have shown in the velocity profile. But the temperature profile only can be obtained with LYT model. The longitudinal temperature is also reproduced with LYT model, and not with Navier-Stokes-Fourier, even if the Holian conjecture is taken. Also, it is very important to note that, first of all, we have a weak shock wave. It means that the Mach number is not too big. It's 1.59. It is a weak shock wave. Then we can expect that almost all models do the task in a good way. But we have seen that it is not the case in the temperature profile. Well, also the Holian conjecture was proposed in the literature according to very big Mach number and was based on simulation calculations. In fact, the original Holian conjecture was proposed for Mach numbers around 130, and we have 1.59. However, in the literature, there are not any question about the validity of Holian conjecture for low Mach number. So the application we have done here for Mach number is not questionable, though it was proposed for a very big Mach number. Also, the temperature provided by Munst were measured. What Munst and Harnett measured was the distribution function for the velocity, but the temperature profiles were calculated taking the velocity distribution function and calculating the momentum, some momentums of this distribution function, which gives them the temperature profile. So in a certain way, the temperature profiles or the experimental profiles for temperature given by Munst are somewhat indirect. However, is the only ones existing for the temperature profile. In the case of the velocity profile, there are a lot of experimental data, somewhat old, but are a lot of them, but not for temperature. It seems that temperature profiles are not so easy to measure. And so we have taken the only ones existing in the literature to do this kind of comparisons. Also, a very important thing is that Holian conjecture and our model, LYT model, take into account the lack of isotropy in the system, which is the lack of isotropy in this problem. Well, there is a direction in the system which is a preferred one, which is the direction of propagation of a wave, which is the x-axis in this case. This is the characteristic shared by the Holian conjecture, where it takes the longitudinal temperature along the x-axis, the propagation axis, and our model, which takes also this property to propose the existence of cross effects between fluxes and forces and thermodynamic forces to have the constitutive equations in this model. This is a very important thing, and we have seen that with this model, which takes into account the lack of isotropy in the system, is important in shock waves to calculate the shock wave profiles. Otherwise, we can reproduce the experimental data mainly concerning the temperature profile. Well, that's all I want to thank. And if there is any question, I think I can answer you.
Thank you, Professor Rosa Maria, for the seminar. Interesting results you obtained with the LIT model, the Linear Irreversible Thermodynamics model. I'm going to open now for questions, and whoever wants to ask Professor Rosa Maria a question, feel free to open the microphone or send a message in the chat.
I have a question.
Yeah.
Please.
Let's go to equations, I think it's 5016.
Well, let me see. Here?
Here, yes, here.
Yeah.
This cross effect, no? Because we have here the visco pressure tensor is a tensor. And the thermodynamic force that you have in red is a gradient, is a vector. How do you connect a tensor with a vector using an scalar? I didn't understand it.
Well, this term, which comes from the viscous tensor, is in fact an scalar, but it is only one component of the pressure tensor, is the component XX. Is the component perpendicular to the plane, to the shock, which is in the direction of X, taken in the direction of X. Then it is a scalar also. So there is no problem with this coupling with a scalar coefficient here, because everything is scalar, because the only direction important here is the viscous tensor along the X component. And also this one, this heat flux has only one component, because there is only a gradient. We are taking one dimension in this for this propagation. So this gradient was just the derivative of the temperature with respect to X, and this one is the derivative, total derivative of the speed with respect to the same X. So the coefficients here can be scalars without any problem. Is it okay?
Yeah, almost. Okay, but if you don't have an scalar, no, if you don't think about the component, but a tensor as a whole, it's not.
Yeah.
It's not correct, no?
Oh, no, sure. If you have really the tensor in a three-dimensional way, you need here a tensor. Yeah, and here you have also a vector, and you have the scalar product of the contraction between the tensor and the vector, of course. And the same here.
Okay.
Because in such a case, this XP will be a tensor, and then you need a scalar product here to construct a vector. But in this case, because you just have the propagation along the X direction, and you are taking the X direction everywhere, all these things are scalar.
Okay. But if you think that it's possible to connect, for example, the viscopressure tensor with the second gradient of temperature, no? What we usually call the Burnett equations, no?
Yeah.
You have results that maybe could be similar, no?
Well, it's not so simple, because when you have Burnett equations, you can take the local equilibrium hypothesis as I did here. You know, and for Burnett equations, the TDS and the production of entropy written as a product of fluxes and forces is not valid. So it is not so simple to extend this to higher derivatives or something like that to to obtain Burnett's.
No, what I mean is you can instead of use the Navier-Stokes equation, you can use the Burnett equations.
Yeah.
No? And
yes, but in the case of Burnett equations, you can do that because the production of entropy cannot be written in this way.
Okay.
Yeah, Burnett equations are not consistent with local equilibrium.
Okay. And I have one question more.
Yeah.
If you go to equation 10,
Here, the Navier-Stokes-Fourier.
okay. These equations follow when you insert the constitutive relation 9 into the conservation equations, no?
Yeah.
And you have here a viscosity, no? This eta asterisk.
Yeah.
Of course, this is not a linear equation, no? Because the viscosity depends on temperature, no?
Yeah.
But it's possible to introduce. It should be possible to introduce a space variable that taking into account the viscosity in order to make this term, this eta asterisk equal to 1.
Equal to 1, but
if
I do that,
it should be equivalent. No, you can define a S variable that is the real variable divided by eta or something like that. And then when we introduce the dimensional variables, this eta asterisk will be 1.
But what happens with the temperature dependence in ET star?
Will be the same thing, no? In order to make this,
I'm afraid I don't understand your observation.
Here, for example, let's go to equation 9, okay?
Yeah.
Equation 9. You have here the visco pressure tensor, no?
Yeah.
Then you can define a variable S, so that you can write the derivative of U with respect to S, the derivative of X with respect to X, and this derivative of X with respect to X are you set as 1 over eta. So I'm defining another length variable, then the eta disappear from the constitutive equation.
Yes, but eta is not a constant.
Okay. In this case, no problem. So I think that the only problem that we'll probably have is we have to return to the original variable, no? So
we have to return to all of this.
Because maybe you can solve equations 10 and 11 in a more easy way. Maybe we can find a analytic solution, no? Because you are solving that numerical, no?
Yes, of course.
Well, I'm just thinking about it.
That there exist exact solutions for these equations. When you have here the Prandtl number equal to 3/4, and the 3/4 for Prandtl, and you have taken this viscosity with an index which is 0. It means constant viscosity. 1/2, which is hard spheres, and Maxwell molecules, then these cases corresponds to a very particular exponent sigma. And can obtain an exact solution of these equations, both equations. But Prant equal to 3/4, it's not a very realistic number compared with experimental data. No matter that, Becker obtained the first exact solution for the cases I have just mentioned. And we, Francisco Uribe and me, we have obtained exact solutions when the index sigma is a natural number, any natural number. And we can obtain the exact solutions for these equations, but I have just said Prant equals to 3/4 is not a very realistic number for when compared with experiments.
Is the so-called Becker approximation, no? Something like that, no?
Well, it's the Becker solution.
Yeah, Becker solution.
It's an exact solution of the equations.
Okay. And may I ask you one thing more?
Yes, of course.
You have here the Mach number.
Yeah.
Where is the Knudsen number?
Well, it does not play a very important role because we are assuming that a continuous description is valid. So the Knudsen number is in the interval where you can approach, which is a hypothesis in all these models. You can avoid the rarefied effects in a certain way. Well, to consider a continuum approach for these cases is somewhat difficult to accept. In fact, a lot of work has been done on the kinetic basis because the Knudsen number is not so small to make a reasonable approximation with continuous equations. No matter that, in the literature, the continuous model are worked for this problem. What we did.
Okay. Okay, thank you, Rosa.
Okay, there's no more questions.
Good afternoon. I would like to ask a few questions. May I?
Please, Felix.
Yes,
Okay.
please.
Thank you. First of all, I would like to thank you for the interesting talk. And my question about the equation 17. The question is, how did you obtain the expression for LPQ 17?
Well, just making a dimensional analysis of coefficients.
Just dimensional analysis.
Yes, just dimensional, and we found that this is the convenient way to obtain the dimensions correct with A2 as a constant.
I see.
But it is just dimensions.
Okay. But probably there is another combination of these variables that have the same dimension. It could be, or you are sure that
well, you can use the thermal conductivity and Prandt's number, but I think it's equivalent.
Yeah, probably yes. Okay, and concerning the viscosity, you mentioned that there are many ab initio results, and really there are many nowadays. There are reliable results on viscosity with precision. What? Sorry. With high precision. Let's say the numerical error 10 to minus 5, 10 to minus 6. So why did you need to use shock wave in order to fit this sigma in the parameter sigma in the viscosity?
No, in fact, the viscosity index is fit with a possibility are the ab initio results for the viscosity directly.
Okay. What results did you use?
Well, we use well, we have used several in this work. We use well, let me find it.
I didn't see.
It's 0.647, I think.
Yeah, yes, but what source, what paper did you use in order to come to this value of sigma?
Oh, this is difficult. I don't remember.
Okay.
My memory is not so good.
Okay, okay, no problem, no problem. I know
Okay.
there are really several papers about
Yes.
this, and they
Yes.
also when I calculated this viscosity index, I found that it is not exactly constant. It's also slightly variable. Okay.
Yes.
One more probably comment about Onsager reciprocity relation.
Yes.
When you wrote LPQ equal to minus LQP,
Yeah.
really it is not exactly Onsager relation. It is Onsager-Casimir relation, because
yes, you are right. You are right. In fact, it's Onsager Casimir, but it was somewhat difficult to mention all that. Yes, it's Onsager Casimir. Yeah, of course.
Casimir generalized the results
Yes.
by Onsager, and then he showed that sometimes it can be minus, sometimes it can be plus.
Yes, I agree completely. Yes, thank you.
In this case, the Casimir. And just to inform you, just to let you know that we calculated the shock waves, the structure of shock waves for several gases, including helium, neon, argon, krypton, and so on, ab initio. And
yes, I think I know your work. However, the position coordinate is different than ours, so we have to translate this your results into our units, let us say, and it was somewhat more difficult to do that than a direct fit. Sorry,
so,
it can be done. Yes, of course.
If you need some help, I can help you to transform your notation to our notation. It's really they are similar to each other, and then it will be interesting to compare, because we calculated for different values of the Mach number, including 1.5.
Yes. Yes, of course. I acknowledge your offer, and I hope we can do some messages to do that. It will be great.
Okay. I would be glad to help you. And what about mixtures? Can you model shockwave in mixtures?
Not yet.
Not yet.
We want to do that, but we have not done yet.
Okay, but it would be appropriate some cooperation, right? Since we did by other methods.
Yeah.
Interested that you make a model following your methods, and then to compare with our results, which are also published recently.
Yeah, that will be great if you can tell me your email. We can make some content to do that.
Okay. I will take your email from the organizer, and then I will let you know my email.
Yes.
Thank you very much.
Yes, thank you. Thank you, and we hope we can collaborate soon.
Thank you.
Thank you.
Sure, Felix. We send you her email. Thank you for the questions, and any other questions? Okay, if there are no more questions, thanks again, Professor Rosa Maria, for accepting the invitation and also for the presentation in our department.
Well, I'll be very glad to see you soon. And well, if you want to do some more questions, you have my email, and we can do everything you want.
And it's a very pleasure to meet you and an honor for us.
Yes.
Okay.
Thank you again.
Thank you all for your attention, and thank you for the invitation. Bye-bye.
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 Thank you, guys.
See you.
Bye-bye. Thank you, all of you.